Welcome to the Deep Dive, the show where we take a stack of fascinating sources and distill them into the essential knowledge you need to be truly well-informed. Today, we're plunging into a topic that, well, sounds like something ripped from a sci-fi novel, but is rapidly becoming today's reality. We're talking about artificial intelligence, not just solving problems, but actively engaging in scientific discovery itself, specifically within the world of machine learning.
It really is a profound shift, and in this deep dive, we're going to explore how these AI research agents are being built, how they're being refined, basically to automate the entire life cycle of machine learning models.
The whole thing, from design to training.
Exactly. From initial design, implementation, right through to the training process. We've gone through some, well, pretty cutting-edge research here to bring you the latest breakthroughs and maybe some surprising insights into making these digital scientists smarter and more effective.
Okay, so our mission then is to unpack all this complex material for you, our listeners. We want to pull out the most important nuggets of knowledge, maybe give you a genuine aha moment or two, something that makes you see the future of AI in perhaps a totally new light.
Yeah, you're definitely about to get a serious shortcut to being well-informed on this. It's moving fast.
All right, let's get started. So maybe we can start with the basics. At its core, science has always been about search, right? Searching through a huge landscape of hypotheses and then, rigorously testing them.
That's the fundamental idea. And now AI is stepping into this arena. It offers just immense potential to automate this entire discovery process.
It's like having these, tireless digital researchers working 24/7, exploring possibilities maybe no human team ever could.
That's a good way to put it. These AI agents can iterate on ideas much like a human scientist would, constantly refining solutions until they hit some desired outcome. But, and this is the key challenge, improving these agents isn't as straightforward as you might think.
Okay, why not?
Well, their designs often entangle several critical performance factors. It's all kind of mixed together. We're talking about everything from the abstract algorithm design, the high-level strategy,
Right.
down to the concrete implementation, the actual code, and even how effectively they use the computing power they're given. This entanglement makes it incredibly difficult to pinpoint exactly what's driving any improvement.
Ah, I see. So it's not just one simple dial you can turn up. It's like a whole stack of interconnected elements. The source material actually uses a great analogy for this, doesn't it? The pyramid?
Yeah, the pyramid analogy is perfect. At the very bottom, you have the compute resources. That's your raw horsepower.
Okay.
Then above that, the environment where the agent does its work. Then the evaluation signal, how it knows if it's doing well.
Kind of.
Higher still are the operators. These are the functions that actually make changes, that modify the solutions. And then right at the top, the search policy, which is how the agent, explores different possibilities.
And the key point of the pyramid is,
The key point is that gains only really happen if no single layer bottlenecks the benefits from another layer. So, for example, if your operators aren't very good, even throwing more compute power or a much smarter search strategy at the problem, well, it just won't yield significant improvements.
that makes sense. Everything needs to work together. So how do they actually test these agents, put them through their paces?
They use a really formidable proving ground called ML-bench. This is a benchmark where these AI agents compete in actual Kaggle competitions.
Real-world machine learning problems, then.
Exactly.
Yeah.
Real-world problems. And their performance is measured by a medal success rate, just like the human competitors on Kaggle.
Okay, and before this new research, what was the leading approach?
The previous state-of-the-art on MLE-bench was an agent called AID. It was driven by a large language model, an LLM, and it framed the problem-solving process as a kind of tree search over Python scripts.
Okay.
And while AID got strong results, the paper points out that it didn't really manage to disentangle all those performance factors we talked about.
Ah, the entanglement problem again.
Right. So it was hard to understand why it performed well or where exactly to focus efforts to improve it further. It was a bit of a black box in some ways.
Okay, so we understand the basic challenge and the previous leader, AID. Let's maybe dig into the components of these agents a bit more formally. You mentioned they can be seen as a search algorithm with two main parts.
That's right. Broadly, you have a search policy. This is how the agent navigates through that huge space of possible solutions. It's the explorer, the strategist.
And the second part.
The second part is the operators. These are the functions that actually do the work. They iteratively modify existing solutions to generate new ones.
So in AID, What did those operators look like?
Well, they had things like a draft operator to create an initial solution script, a debug operator to fix errors it found,
Makes sense.
and an improve operator to try and refine an existing script.
Hmm.
The agent basically picks a solution, applies one of these operators, runs the code, evaluates the result, and decides what to do next.
Okay. Now, you mentioned earlier there was a really pivotal discovery here. What was that?
Yes, this was, I think, the crucial insight. When the researchers took AID's original operators, the ones it came with,
Yeah.
and tried pairing them with more advanced search policies, things like Monte Carlo tree search, MCTS, or evolutionary search, which you'd expect to be much more powerful.
Right. You'd expect a boost.
Exactly. But they got no significant performance advantage, zero. It turned out the bottleneck wasn't the high-level search strategy at all. It was the fundamental operators themselves, how the agent was actually trying to change the solutions.
Wow. So the fancy search algorithms were essentially wasted because the tools they were using, the operators weren't good enough.
Precisely. It was a very counterintuitive finding at the time, and it got reinforced by something else they found in an ablation study, basically, where they removed parts to see what happened.
What was that?
AID had this memory operator. It was designed to summarize past attempts, designs and scores, and add that summary to new props to give context.
Seems sensible.
You'd think so, but removing it had almost no impact on AID's performance, so that really drove home the point.
Yeah.
The existing operators, even the memory one, needed a fundamental rethink.
Okay, so if the operators were the bottleneck, the clear next step is build better operators.
Yeah.
And maybe a better place for them to work.
Exactly. And that leads us straight to the breakthrough. The AI Research Agent Dojo, or ARA Dojo.
ARA Dojo, what is that exactly?
It's a scalable, customizable framework. It's specifically designed to be the ideal environment for these agents. It gives them robust interfaces to computing resources, and very importantly, it uses something called Aptainer containers.
Containers, like Docker.
Sort of, yeah.
Yeah.
Aptainer provides complete isolation. Think of it like creating a perfectly sterile, identical laboratory environment for every single AI experiment.
Ah, so you guarantee reproducibility. You know the results are reliable.
Exactly. It removes a lot of confounding variables.
And what was the impact of just using this new environment, even before changing the operators?
The impact was, frankly, stunning. Just implementing AID's original baseline agent, but running it inside this new IRA Dojo environment. Its metal rate jumped significantly. It went from 35.2% up to 45.9%.
Wow, that's what, over 10 percentage points?
Yeah, a 10.68% absolute increase, which is about a 30% relative improvement. So just the cleaner, more reliable environment made it the new state-of-the-art before they even touched the operators.
That really underlines the importance of those foundational layers in that pyramid analogy you mentioned. The environment matters a lot.
It absolutely does. But of course, the core improvement did come from the new operator set, which they called OARA.
Okay, OARA operators, how did they differ? What was the philosophy?
Well, they built on AID's concepts, still had things like draft, improve, debug, but they focused on maintaining cleaner context for the LLM and encouraging more structured reasoning and, crucially, strategic diversity in the ideas the agent generated.
Okay, cleaner context, structured reasoning, diversity. How did they achieve that? What were some of the clever changes?
They implemented a few really key ideas. First one was prompt adaptive complexity.
Prompt adaptive complexity. Sounds fancy.
It's actually quite intuitive. It's basically a dynamic cue they give to the draft and improve operators. It guides them to generate ideas of the right level of complexity for the current situation in the search.
How does that work?
Well, for example, if the agent hasn't explored much yet, if there are only a few child solutions branching off the current one, it's prompted to create simpler solutions. This prevents it from, over-engineering things too early.
Right, don't build a spaceship if you just need a bicycle.
Exactly. But if there's already been a lot of exploration from that point, it encourages more advanced or complex ideas. It adapts.
That's smart. It's like giving the AI a bit of engineering judgment.
Right.
What else?
Second big change was scoped memory. Remember how AID's memory operator wasn't really doing much?
Yeah, the one that summarized everything.
Right. The new ORI memory operator was modified to retrieve only relevant information, depending on the task.
Ah, targeted retrieval.
Precisely. So for the draft and improve operators, where you want new ideas, it retrieves sibling memories, information from parallel attempts to promote diversity.
Okay, see what others are trying.
But for the debug operator, it retrieves ancestral memory, what happened leading up to this point, to help the agent understand the history of fixes and avoid getting stuck in, undo, redo loops.
That makes a lot of sense. Prevents it from getting overwhelmed with irrelevant info or stuck in a rut.
Exactly. It prevents context overload and a problem they call mode collapse, where the agent just keeps generating the same kind of idea over and over.
Like that chef who only makes pasta.
That's a great analogy, yes, no matter the ingredients. And the third key thing was think tokens.
Think tokens. This one really caught my eye. What's the deal here?
Yeah, this is clever. The large language models, the LLMs doing the work inside these operators, were explicitly encouraged to use thinking tokens. Essentially, they were told, okay, before you give the final answer, do some reasoning, some reflection, some structured thinking internally.
Like showing your work in math class, but internally.
Kind of. And crucially, these thoughts are then stripped out before the final output, the Python script usually, is generated, so they remain invisible to the other operators or the main search process.
And did it make a difference? Did they actually think more?
Apparently so. The research showed a twofold increase in the number of completion tokens used by the ARA operators compared to the old ones. This strongly suggests, well, deeper internal thought processes were happening before they generated the solution.
That's fascinating. It's almost like they taught the AI how to think about the problem, not just spit out an answer. Do you think this internal thought could lead to more creative solutions down the line?
It certainly opens that door. Giving the AI that space for internal reasoning, yeah, it might let it stumble upon novel connections or solutions that aren't immediately obvious just from the prompt. It's a really interesting direction.
Okay, so we've got the new ARA Dojo environment. We've got these much smarter OIRA operators with adaptive complexity, scoped memory, think tokens. What happened when they put it all together? Did the operators alone make a difference?
They did. They tested an agent called AirGreedy. This used the new OIR operators, but still used just a simple greedy search policy. Always pick the best looking option right now.
Okay, so operators improved, search strategy is still simple.
Right. And AirGreedy directly outperformed the old AdaGreedy baseline. The medal rate went from about 39.8% for AdaGreedy up to 45.5% for AirGreedy.
Just from the operator.
Just from the operators. That's a solid 14% relative improvement.
Okay, now what happened when they brought back the advanced search strategies? The ones that failed before?
This is where the breakthrough really comes into focus. With those improved OIRA operators in place, now the advanced search methods like Monte Carlo tree search and evolutionary search finally delivered. They yielded significant performance gains.
So the operators really were the bottleneck. Once you fix them, the smarter search could actually do its job.
Exactly. The bottleneck was removed, and the advanced search could finally shine. The top performer became AirAmps. That's the new ORA operators, combined with Monte Carlo tree search. It achieved a new state-of-the-art on the MLE-bench light benchmark, hitting an average medal rate of 47.7%.
Okay, 47.7%. That's the new high score.
That's the new high score. And the key takeaway from all this investigation is really the importance of jointly considering everything. The search strategy, the operator design, the evaluation methodology, even the environment. It's the interplay between all these components that's critical.
It's not just about having one brilliant piece, but how they all fit and work together like a well-oiled machine.
Precisely.
So these AI agents are getting seriously good at solving machine learning problems on these benchmarks. But you mentioned there's another challenge, a hidden one, something called the generalization gap.
That's right. This is a really important, maybe subtle issue. The problem is that these AI agents, as they search, they steer themselves using validation scores.
Okay, what are those?
They're essentially proxy metrics. The agent runs its code on a portion of the data, the validation set, and gets a score. It uses that score to decide if a solution is good and where to search next. It's trying to optimize based on what it thinks is the best solution according to this validation data, but its final performance, how it's ultimately judged in the competition, is measured on a completely separate, held-out test set that it's never seen before.
Okay. So the score it uses to guide itself isn't the same as the score that really counts in the end.
Exactly. And that difference, that discrepancy between the agent's perceived performance on the validation set and its true performance on the unseen test set, that's the generalization gap.
Okay, I think I get it. So the AI might be optimizing for a signal that doesn't perfectly match reality? What's the consequence of that? Does it just waste time, or can it lead to bad solutions?
It can lead to something called systematic overfitting. This is where the agent's validation score keeps going up and up. It thinks it's getting better and better.
Right.
But in reality, its true ability to generalize its score on the unseen test data might actually plateau or even start getting worse.
Oh, wow. So it's like a student who keeps studying really hard, but they're studying for the wrong test. Their confidence goes up, but their actual exam score tanks.
That's a perfect analogy. It's wasted effort, essentially, because the solution it thinks is great won't actually work well on new, unseen problems.
How significant is this gap? Is it a minor annoyance or a major hurdle?
It's actually quite significant. The research quantified this. They looked at an oracle scenario,
An oracle.
meaning what if the agent could magically know the true test score for every solution it generated and pick the best one based on that perfect knowledge?
Okay, the ideal scenario.
Right. In that ideal scenario, the medal rates would jump by an astonishing 9 to 13 absolute percentage points, depending on the specific agent.
9 to 13%. That's huge. That's a massive amount of performance left on the table because of this gap.
It is. It shows how much potential is currently locked away due to this difference between validation and test performance.
So how do you bridge that gap? Is there a practical fix for this studying for the wrong test problem?
Well, the good news is that most of this gap can actually be closed. It comes down to having more robust strategies for final node selection.
Final node selection. Choosing which solution to submit at the end.
Exactly. Instead of just blindly trusting the single highest validation score, which might be noisy or misleading,
Yeah.
a simple and very effective remedy is just to hedge your bets. Select multiple promising nodes based on their validation scores.
Like take the top few.
Precisely. They found that by simply submitting the top 3 candidate solutions ranked by validation score and then letting the test set decide which of those 3 was actually the best,
Uh-huh.
the agents recovered an additional 10% of performance on average.
Wow. Just submitting the top 3 instead of the top 1 makes that much difference.
It does. It's a straightforward but remarkably effective way to mitigate the noise and uncertainty inherent in those validation scores.
That's a fantastic practical takeaway. It's like instead of just trusting one expert's gut feeling, you get your top 3 experts to present their best ideas, and then you see which one actually works best in the real world.
Exactly. It's a simple form of ensembling, really.
Now, these benchmarks, like Kaggle, usually have time limits, right? Like 24 hours or something.
Typically, yes.
What happens if you just let these agents run for longer? Do they keep improving indefinitely?
That's a great question, and they did look into that. While the main results focus on those 24-hour competition-style limits, they ran experiments letting the agents search for much longer, up to 90 or even 120 hours.
Okay, several days.
And they found that the agents do continue to improve well beyond that 24-hour mark. This suggests there's still quite a lot of value in longer, more sustained exploration if you have the compute resources.
Interesting. Does that mean that really advanced search methods like AIRX just keep pulling further ahead over those longer runs?
Well, here's another interesting twist. Over those very long runs, AR-greedy, remember that's the one with the good operators but the simple greedy search?
Right.
It actually continued to improve steadily, peaking somewhere around a 53% medal rate after maybe 90 hours. That's another 6% absolute improvement over its 24-hour peak.
So greedy search kept finding gains.
It did. But AIRX, the one with the sophisticated Monte Carlo tree search, while it was strongest initially, over those very long runs, it actually started showing signs of that systematic overfitting we talked about. Its performance eventually deteriorated slightly.
Huh. So even the best search strategy can eventually fall victim to the generalization gap if you run it for too long, without addressing that core issue.
It seems so. It really highlights that the generalization gap remains a fundamental limitation, especially over extremely long time horizons, even with sophisticated search. You can't just run it longer indefinitely and expect things to keep getting better if you're optimizing for the wrong signal.
That's a crucial nuance.
Yeah.
Okay, looking ahead then, beyond just running longer, what are some of the exciting future directions for this kind of research? Where does it go next?
Well, there are several really promising avenues. One is the idea of using full-fledged AI agents as operators.
Agents as operators. So an AI operator calls another AI to help it.
Kind of, yeah. Imagine a specialized, smaller AI agent whose job is just to perform the improve function or the debug function, almost like having specialist sub-researchers within the main agent.
That sounds potentially very powerful.
What else? There's also work on fine-tuning the underlying large language models specifically for these kinds of scientific discovery tasks, making the brain of the operator even better suited to the job.
Right, tailoring the LLM itself.
Exactly. Then there's scaling search even further, using even more computational resources than they tested here, and critically continuing to tackle that ongoing challenge of data contamination.
Data contamination, you mean making sure the AI hasn't accidentally seen data similar to the test set during its training?
Precisely. It's a subtle but important issue to ensure the performance we measure is genuine and not just because the AI got a sneak peek at the answers somehow.
Got it. Lots to explore still. So let's try and recap our deep dive today. We've seen that automating machine learning engineering isn't just some future dream, it's happening now, and it's advancing really rapidly.
Yeah, and the real power, the real breakthroughs seem to come from a combination of things. These thoughtfully designed operators that encourage structured thinking and diverse ideas,
Right, the OARA operator.
combined with smart search strategies, but only once those operators are good enough. And then critically understanding and finding ways to bridge that generalization gap.
That difference between what the agent thinks is a good solution based on validation data and what actually works in the real world on unseen test data.
Exactly. Getting better at final node selection, like submitting the top three, is a big part of closing that gap right now. The ability of AI to really accelerate the process of scientific discovery is becoming much more concrete with each of these breakthroughs in agent design.
It really feels like we're on the cusp of something significant, which leads to maybe a final thought for our listeners to ponder. As these AI agents become increasingly adept at scientific discovery, not just in ML, but potentially beyond, what new breakthroughs in areas like medicine or material science, or maybe even tackling climate solutions, what might be just around the corner thanks to these tireless digital researchers?
It's a truly exciting prospect to think about.